let us discuss quantification of basic events. Today we will be considering the hazard rate or hazard function. The content of today's presentation is introduction, failure rate and or hazard rate, example, bathtub curve and one tutorial. So, you just let us understand what we have discussed in last class, because this class has good relation with my last class. In last class, I have shown you the concept of reliability, then failure distribution, So, we defined reliability as RXT, failure distribution as FXT, and then we have gone to probability density function, which we defined as small f x t, where is t is basically the time to failure. We consider non-repairable units, Okay. And and with different formula, starting from the scratch, we have defined what is RA, RT, FT and small ft. So, for the time being, suppose let t equal to 0, and then suppose you are going to equal to 1, 2, something like this, let it be maybe 100 units of time. Then let you are conducting an experiment where you are putting suppose n number of identical units into operation, and then you are finding out, suppose let L equal to maybe n equal to maybe 1000, and then what you are doing, you are finding out that what is the number of items surviving after certain time interval. For example, at t equal to 0, the if I say Ct is basically the survival units, then here it will be n, which is 1000. And in this manner, suppose in the next unit is 900, then 850. So, like this you found out that at the 100th time, that is 0. So, then number of units survived, that is Ct by n, that is your RXT, reliability. So, it will start 1000 by 1001, then this is maybe 0.90, 0.85, in this minus, finally it will be 0. Okay. So, then what we have seen? We have seen FXT, which is basically 1 minus RXT. So, 1 minus this will be 0, this is 1 minus 0.9, then 0.10, 1 minus 0.85, that is 0.15, like this, and finally it is 1.0. Then you have seen that FXT, this one is nothing but what you have done, that number of units fell in n t plus delta minus n t by n. So, if I consider these two, that means 100 units fell, and then out of 1000 units, and that manner you have computed the FXT. So, when you go for the second time interval, you will consider the difference between these two. Third time interval, like this, FXT also we have computed. Today we will be discussing that another important concept called hazard rate. Hazard rate. this hazard rate, and with example we will be discussing. Finally, that bathtub curve will be discussed, and then one tutorial you will see. So, what is hazard rate? Hazard rate is, or hazard function, it is basically the probability of failure of a component within very short period of time, let t and t plus delta, given that the component survive till t, till time unit t. It helps in identifying the health of the component in terms of increasing the constant and decreasing failure rate, that also we will see later on. See what is hazard rate here. Be careful. We are saying that hazard rate is probability of failure per unit time at time t. That means we have some timeline, that is t, and suppose this is our hazard rate h t. What we are basically interested to find out, suppose the unit survive till time t, then we are creating another time interval, that is delta. So, this point is t plus delta. Now, this is basically that probability that the unit survive up to time t, it will basically fail within this small interval delta t. That is what is the hazard rate. That is why this is also known as failure rate, or more precisely instantaneous failure rate. Instantaneous failure rate. Okay. So, this delta is very small amount of time, very small time. Then by this definition, if we denote that R x t is the hazard rate, let it be R x t is the hazard rate, then it is number of failures during this period of time, and we are saying that per unit time. So, that means divided by delta, if we put here, we can multiply delta in this side, no problem. So, number of unit failures during t plus delta t by number of survival at this time period. So, that means R x t into delta, the time period, is this, because we are interested in per unit time. In delta time, what is the units fail? That number of survive here and number survive here, the difference will be number of units fail in delta time. So, then per unit time it will be by delta. So, instead of writing here by delta, you are writing here multiplying this side. So, no problem. So, then what is the number of failings at this point in time? That is n t. What is the number failing? That is n t plus delta. So, number of failures during this is n t plus delta minus n t. Then number of surviving at this place is C t, that is what we have seen earlier. So, then this one can be written. So, this can be written like this: n t plus delta minus n t by C t. So, this can be written like this, again dividing n capital N, which is the number of units that put under test at the time t equal to 0. So, if you divide this, then you see what you are getting: R x t delta equal to this f x t into delta. Where from this delta is coming? Suppose if you consider delta equal to 1, what I have given in few minutes back, I said that n t plus delta minus n t by this will be your f x t provided delta equal to 1. But we do not know whether that delta 1 or delta less than 1, but it is a positive quantity. So, then if it is delta time, then delta will be multiplied here. So, that is what n t plus delta minus n t by n will be f x t into delta. So, that is what is written here. and this one is Rxt, the reliability part we have discussed earlier. So, this is Rxt. Now, this delta and delta will be cancelled out. So, what is Rxt? Rxt is Fxt by this. Clear? If it is not clear, let me explain again that our Fxt will be the density, that n t plus delta minus n t by n into delta, because this is delta. So, now, so you have the quantity top side, that n t plus delta minus n t by n. So, if I remove this, I have to write like this. This is what is written here. So, then this much is okay. Next is that where how you are getting this, because see ultimately what is Fxt? Fxt is derivative of d by dx di dt d by dt into its cumulative function Fxt. What is d that Fxt? That is 1 minus Rxt, because Fxt plus Rxt equal to 1. So, then if you take derivative, this will be 0 and this will be minus d by dt in Rxt. So, if you write Fxt in this form, then Rxt will be 1 by capital Rxt into d capital Rxt by dt. So, that means the hazard rate in terms of reliability. Okay. So, that is the definition and the derivation of hazard rate. Interestingly, it basically gives three important explanation. One is increasing failure rate, constant failure rate and decreasing failure rate. So, depending on the this Rxt, if it is increasing, then the conditional failure probability increases with age. We said that this survive up to time t, and then what is the failure probability, that it will fail in the next unit of time, within next unit of time. So, conditional to this survival, this will the failure rate will increasing. That means, failure rate increases, probability of failure increases with increase in age. If it is decreasing failure rate, probability of failure decreases with units age. If it is constant failure rate, that means there is no change in the probability of failure with age, at least for a particular period of time. So, that is what is the explanation of hazard rate, but hazard rate is better understood by hazard by bathtub curve. So, that we will describe, but before that you please see one tutorial here. We have considered t equal to t0 to 100. So, 100 different units. Please see that first 0 followed by 1, like this up to 5, the change is 1 unit, and after that the change is 5 unit. So, then at the beginning, the number of units put under operation was 1050, and then slowly as that age increases or time increases, the number of units starts failing, and at 1 unit of time, that means the number surviving is 1020, and this we have discussed earlier in this manner. So, then the number of units failed during in between t equal to 0 to t equal to 1 is 30, number of units failed in between 2 and 1 is 20, like this. Then what is our Ft? Here you will have confusion if you consider delta equal to 1 all the time, then what you will do, n t plus delta minus n t by original that number put under operation, that you will divide. This will work up to this. After that what happened here what happened, this minus this is 5 unit difference. So, delta to be put. So, that means Ft here is n t plus delta minus n t by delta into n. This delta will be 1 for the first 5, after that it will be delta will be 5. So, in this manner we have calculated. So, once f t is calculated and also you know the C t, you know the R t also. So, what is R t? R t is basically C t by n. So, this. Now, if I know R t and if I know small f t, you know hazard rate, because hazard rate R t is that density by reliability, because this is the probability of failure or other way it is basically it is failure density within certain period what is the how many fails, and then R t is the survival function, this is the conditional part. So, you have f t, you have R t. So, small r t is f t by capital R t. In this manner you have computed, and I am sure that you all will be able to compute this. You practice, use Excel sheet and take the same data. So, what data you require? You require only this T and CT data, rest of the data will be derived from or computed from the C and T. So, you got now the hazard rate or hazard function or instantaneous failure rate, and sometimes we say also failure rate. In many books it is written failure rate. So, then if you plot this, we have plotted this hazard rate and we got this kind of curve. So, if you see this curve, here what happened from this point, okay, this axis little actually no, this is the region. Okay. So, tradition in general, when you talk about the life cycle of the SIS unit, usually it will be like this. It will be like this, but from our data we got this blue colored that curve. But if we consider the life cycle of the unit, that then you will find out the hazard rate will be like this. If hazard rate is like this, then there are 3 regions. One region, this one is the decreasing failure rate, this region is known and that is basically we say early failure zone. And then after that what happened, why this early failure actually takes place? This is basically the DFR characterized by early failures or infant mortality, and then followed by there will be a long period of time when the hazard rate will be constant. So, this is decreasing failure rate, here constant failure rate, and this is increasing failure rate. So, this constant period rate, that period will be quite large compared to early failure rate and that is the burnout phase. So, then last phase will be the increasing failure rate. This increasing failure rate is basically wear out or burnout failures, because that is the end of the life of the unit under consideration. So, that is the beauty of hazard rate, because it gives you the bathtub curve, and then you initially when the product under operation, what will happen because of basically that infant related, means some kind of I can tell you that some kind of test problem, some kind of quality check problem, the product will face more failure initially, and then slowly those quality problem will be checked and finally it will be rectified, and then the failure rate decreases very quickly and reaches to the constant failure rate, which is the useful life, and then this will follow, and finally here because of age effect, because of aging effect, the the component or the unit will very quickly undergo to death. So, that the three different region you will get in bathtub curve. You may ask us that in the data what we have plotted, this portion is not there. It's although data is hypothetical, but if you in practice you got this kind of plot, then that means the component early failure time, that is not taken into consideration in the analysis. Okay, because the unit is very well under useful period of time, most of the units, and some units are under the wear out phase. So, that is what is the meaning. So, what is let me read out little more. As I say that DFR is characterized by early failure or infant mortality. CFR is characterized by a constant, this is time independent failure rate, and IFR is wear out failure rates. Now, what are the reason for early life failures? As I told you, they are basically, you say they are not detected during testing or quality control procedure, and the defect may arise from poor material, assembly, installation and other causes not covered during testing. That is the reason you get initially little more failure, then obviously reasons are found out and rectified and failure rate decreases. So, the constant failure rate is called useful life region, very important, and this is the time when the product or the unit is under full operation, under full utilization. And the increasing failure rate near the appearance of possible aging phenomena. So, why? Because of definitely age means wear out, worn out phase. Chemical, physical, environmental factors are responsible for such wear out. Also, corrosion and other things will be responsible. So, what we have discussed? We have discussed hazard rate, and we relate it to the your failure density as well as reliability. And then we have shown you through a tutorial that how the hazard rate is computed, and then we have also seen here that hazard rate is typically a bathtub curve, and it is you will get this bathtub curve if you have data for the system life cycle. And there are important issue is that the early failure rate will be quickly decreasing, and this is because of the testing and quality problem, and the useful period of life or useful constant failure rate period will be very lengthy, because this is the period when the component or unit or the system is under full utilization. And because of the age and maybe overuse, stress, the environmental, chemical, all other factors reason, what will happen, the component, unit or system may undergo wear out phase, and then what will happen, it is basically reaching towards the death. You have to dispose of the unit from the operation. Okay, so that is what is the meaning of hazard rate or hazard function. So, then let me summarize this, what you have learned so far in quantification. So, in summary, you have learned that x, that what is the CDF, cumulative distribution function. That means the what will happen, the if x is a random variable which denotes that the component time to failure, then probability that x fail within time t, that is what is fxt, which is CDF, cumulative distribution function. Then you have understood Rx, which is reliability of the component, unit or system. Reliability means the probability that the unit and unit will operate for the intended period of time under given environmental condition, because for which it is intended to work. So, that is what, that is the probability that the random variable x, which is basically time to fuel, it exceeds the time or given time t, then this is nothing but 1 minus the cumulative distribution function, because ultimately for our component or unit is two state system, either it is surviving or under it's failed. So, the fxt and rxt combination, the sum of these two will be 1. Then what happened? We have shown that you have done a random experiment, and in this experiment n identical units are put under test, and then you observe that how many surviving after certain time intervals, and that time intervals is Ct, which is basically Ct may be 0, may be 1 or like this, or T0, T1, T2 like this that time, and then Ct is basically the number of units survive at t equal to 0, t equal to 1, t equal to 2, something like this, and n is the number of units under test at t equal to 0. So, as a result at t equal to 0, rxt will be 1, and slowly it will decrease, and at the end of the life cycle it will be basically 0, but theoretically it is 0. And then you have learned also fxt, which is nothing but the derivative of the cumulative distribution function, and then what happened using this formula f x t plus delta, this is nothing but CDF with reference to time t plus delta, and this is with reference to t divided by delta. So, if you are conducting experiments, you will be having the data available with you. So, that data is n t plus delta, number of units failed at time t plus delta, and minus number of units failed at time t divided by total number put under test and the interval of time for which the delta, that the interval of time you are considering or unit of time you are considering. So, this also we have you know now, and you with examples you know how to compute it, plus rxt, which basically today we have discussed. So, last class we have discussed up to this. Today we primarily concentrate on the hazard rate function, and in last class also I have discussed that what will be the mean time to failure. This is nothing but this or this equation. Okay. Now, this is what is already done. So, in the right hand side there is a figure. You just see the figure. This figure is basically talking about the parameters. Parameters for here we are basically considering repair to failure process. It is basically repair to failure process is equivalent to this is a system here non-repair, only one repair to failure means it is a non-repairable system. It is basically once it fails you have to discard it. So, under parameter estimation, what are the things given? Failure density, it is discussed. We have discussed cumulative density function, we have discussed reliability, we have discussed hazard rate or failure rate, we have discussed mean time to failure. Okay. So, you have done an experiment. So, and from the experiment you will get time to failure data. Then from time to failure data you can develop histogram, and then you can approximate the histogram through some polynomial expression. So, that we have not discussed here. We have basically given a polynomial approximation, we have not discussed here. So, ultimately in the right hand side we are saying that the theory behind the or the computational details behind all those parameters given here. But many a time what happened, you will just take the time to failure data and then you will derive all those things, not the manner we have discussed from the experiment basic, from the basic fundamental or from the zeroth law kind of things of this distribution. So, here what happened, once you have time to failure data, you can plot the histogram. For example, I have TTF data, I can start from 0, 1, 2 like this, and this side there can be frequency, means within 1 unit how many fails, maybe let this 1 to 2 units let this unit fail, 2 to 3 units let this fail, this fail like this. Then this is nothing but the histogram. So, what is histogram? Because your what is the variable x here or t, time to failure. So, time to failure you are arranging them in ascending order, then creating interval. Here we have create interval of 1 unit of time, 0 to 1, 1 to 2 like this. Then you have found out within 1 unit of time how many fails, this is the frequency, and then within 1 to 2 how many fails like this. When you plot this, you will get this that attached bars, that bar 1, 2, 3 like this bar will basically gives you the histogram. Now, if you draw the midpoint of all those bars, you will be getting a curve. Now, here this is almost a straight line, but it may so happen that your histogram will give you a curve like this, or it may give you a curve like this when the midpoint are joined. Then by polynomial approximation we are saying what is the equation of this one. So, if this is t and this one if I say it is f t, then f t can be approximated with in terms of t through some polynomial approximation. For example, if I say that this is the exponential part 1, then you can write that f t equal to maybe e to the power minus lambda t. Okay. So, that can be an equation. So, it is just I am not saying that this may be the equation of this, I am saying this is one kind of, or you may say that it is basically t cube plus a t square plus b t t minus 9, that is my f t. So, this is another kind of polynomial approximation. Okay. So, this is what is the starting of the quantification of basic event, that the how do I know the probability of failure, the hazard function, the reliability and other things. And please go through the book, the 2 books already given here. I hope that you will be able to understand it and you will be able to solve the assignments as well as the examination problems. If you have any query, please put in the discussion forum. Thank you.